let's talk a little bit about the field of something called geometric optics. We can also think of this as being treating light as a ray. So in other words, we're going to treat light as basically going to be like a little arrow. And this little arrow is going to represent the ray aspect of light instead of treating it like a particle. When we're treating light as a ray, we can kind of think of it as having three ways to travel, three ways that light can get around. Our first way to travel is going to be through empty space. This is something we call radiation. So this is how we get light from the sun, how heat energy travels, radiation, just through empty space. We also have light traveling by reflections. And this is really going to relate to the field of studying mirrors. And in particular, a particular law called the law of reflection. And in the law of reflection, we can think about having a mirror. So here's a mirror. We're going to use these little jaggedy hash lines to represent the mirror itself. And I can have some light that comes in. So I'm going to draw a perpendicular line. That's going to be my dotted line. And I have a light ray that comes in at some angle relative to that perpendicular. We'll call that theta with the subscript I, the incident angle. Now, with the law of reflection is going to tell us that this incident angle, whatever this is, this theta I, when I reflect off, my ray aspect of light is going to reflect off at some angle, and that angle of reflection with the two little arcs, we're going to call that theta sub r, is going to be equal to theta sub I. So the angle of incidence is equal to the angle of reflection. This works when your mirror is at an angle too. So maybe I have a mirror that's kind of not just flat on the ground. It's kind of angled a little bit. I draw my perpendicular line. My light ray comes in, hits at some angle of incidence.
I don't understand.
And it's going to reflect off at some angle of reflection. So that is the law of reflection. Theta incident equals theta reflected, where this theta is with respect to the normal or perpendicular to your surface. And then we have a third way that light can travel. Our third way is going to be through refraction. And this is a light ray traveling through a lens or inside of another medium. So light passing from air into water or passing through glass or something like this. And what this says is that we have a law of refraction. And the law of refraction tells us that light changes direction when it passes through something. So when I have light moving, it's going to bend or twist or around something. And the amount of bending that you get is related to something called the index of refraction. And this refractive index depends on properties inside of your actual material. The index of refraction of a material we label with the letter N, and that's equal to C divided by V, where C is the speed of light in a vacuum, so in completely empty space, we're going to divide that by the speed of light in the material. So materials slow down light. And something to take note of is that the speed of light right now, as far as we know in physics, is a cosmic speed limit. We cannot travel faster than the speed of light. So because of that fact, since we can't travel faster than light, the numerator is always going to be bigger than the denominator. So that means that this index of refraction is always greater than 1. And these kinds of numbers, these indices of refractions, you would go to a table typically to find what these numbers are. And we use this index of refraction to figure out how much light bends using a particular law called Snell's law. Snell's law tells us n1 sine theta 1 equals n2 times sine of theta 2. And this relates to light passing between two different medium. So let's draw a line. Let's say I have air up here up top, and I'm passing into some kind of water. So I'm passing through a surface. I first draw a perpendicular line. All these angles are typically relative to a perpendicular. And I have some light that comes in. It comes in at an angle. We'll call this theta 1. And we'll call the index of refraction of air n1. And it's going to refract. It's going to bend a little bit. So we can draw our bending at some angle, theta 2, in the index of refraction of water, which we will label as n2. So this is how the index of refraction works. This is how Snell's law actually works. n1 sine theta 1, the actual incoming ray of light, and the angle relative to the perpendicular, theta 1, in your first medium, equals the index of refraction in your second medium, this n2, and the angle that you kind of bend at when you go into the water. Now there is a special kind of form of refraction, and we'll put that in quotation marks because it's not really special. It's kind of a unique case. The special refraction we call total internal reflection. This has become very popular in the medical fields, where we need to do kind of laparoscopic surgeries and need something called a fiber optic. Okay, so total internal reflection is what you get when your incident angle makes an angle of refraction that's equal to 90 or greater. And this is called going through something called the critical angle. So what does this actually look like? So let me draw a fiber optic. What do all those words that I just said actually mean? So let's say that I have some light ray traveling inside of this kind of wire, this tube, and it's going to hit the edge of this this wire, this fiber optic. Now, I can draw a perpendicular line. Again, we like perpendicular lines for geometric optics. And there's some specific angle. We'll call this theta c, called the critical angle, where the reflection that I get, the refraction angle that I have, is going to be equal to 90. So if my refraction angle is equal to 90, that means that my light angle of refraction is going to be entirely along this surface. So my light actually can't escape out of this wire. And if my critical angle is greater than this, if my refraction angle, incident angle, is greater than this critical angle, then I'm just going to keep refracting into this surface. So if I make this angle just a little bit larger, I'm going to hit my interface and I'm going to bounce in. And I'm going to be stuck in here. So as long as this angle is correct, as long as I'm greater than this critical angle, I'm just going to keep refracting down this, this tube. And I'm never going to escape, so I'm not going to lose any light. This is the way we use something called fiber optics. So So what you can see in this picture right here is this exact thing happening. So my I've got a fiber optic, so basically we can kind of outline this. This is just a wire, and these are the walls of the wire. And I shine a laser in, and as if I have the right materials in my fiber optic, I can shine this laser down, and it's going to hit. So my laser, here we'll draw it in blue so that we can see a little more clearly. And I can draw my perpendicular. So let's draw my perpendicular here. And again, I'm drawing this on an actual image of a fiber optic. So my light ray comes in, and as long as this angle right here, the angle of incidence, is greater than some critical angle, all the light gets reflected in. So none of the light is escaping. So I can't have any light rays actually refracting out. That is not happening. Everything is totally internally reflected inwards. And it just keeps bouncing along the surface, so I can control the path that this light takes. It's extremely, extremely useful, and it's used in a variety of applications. So it's being used to basically fiber optics let you control light paths. You can bend light around corners. Lets us create cool cameras, lets us do surgeries, in particular a field of surgery called endoscopic surgeries. So that's total internal reflection, kind of in reflection, a total kind of special case of refraction. Now there's more aspects of light that we should be familiar with. We should be familiar with the concept of a rainbow. And we all know what a rainbow is. A rainbow is all the colors of light. There's the famous artist Roy G. Biv that kind of represents all the colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. We should all be familiar with that. And when we combine reflection and refraction to get a rainbow, we call this dispersion. So a rainbow is a field of physics, physical phenomena called dispersion, which is basically a combo of reflection and refraction. So we have some terminology in mind, some basics. Now we need to actually know how we use light. And one way that we can use light is through the use of lenses. And there are going to be two types of lenses. There's lenses that focus light to a certain point. Those are called converging lenses. They tend to focus light on the opposite side of where the light comes from. So if I have a lens that kind of looks like this, I have a light ray that comes in from the top and one that comes in from the bottom, and they're going to be focused down to a single point. That point we're going to call F. We'll call that the focal point. That's where the light actually focuses. The other type of lens we have is called a diverging lens. That takes light and makes it kind of diverge away. So we can draw a diverging lens as kind of a different shape. Looks like this. And I have kind of a light ray that comes in and from the top, and a light ray that comes in from the bottom, and the light when it hits the lens is going to actually get dispersed outwards. Okay? And what I do to figure out the focal point of this lens is I imagine these light rays are traveling straight, so I draw a diagonal kind of imaginary line going backwards, and that imaginary line going backwards, that is my focal point. So that's my focal length for a diverging lens. Okay, to figure out how powerful a lens is, we also have an equation that tells us this. P stands for power of a lens, and it's equal to 1 divided by F. And there are some very powerful equations we can use to figure out what light inside of a lens will actually do. So to understand how light works, we need some equations. And to understand these equations, we need to draw some pictures. So to draw pictures of lenses and light traveling through lenses, there are some procedures we follow. First, we draw a nice horizontal line, and we'll call this something called the optical axis. The optical axis is what all elements of your lens system will have on it. We draw some object. So this is something that we're going to use to make an image of through an actual lens, and we'll choose a converging lens for no particular reason. So this object is some certain distance away from my lens. From the middle of my lens, I call that D0, the distance of my object. And to fully describe this object, I also need to know how tall it is, so we can describe its height above the optical axis as HO, the height of the object. And every lens that we have has two particular points. These 2 points are called focal points. It's where the light from the lens actually gets focused. There's a focal point on the back side of the lens, on the front side, the same side of the lens as the object, and then there's a focal point that's equidistant away on the opposite side of the lens where the light will be focused for a converging lens. So we have 2 focal points. So F is something that we represent as a point, and we call this the focal length. That's how far it is from the center of your lens to the point where the light focuses, and that's intrinsic to the lens. Depends on what lens you have. And there is a way that I can figure out where my image is going to form from this whole mirror system. First, I can draw one light ray. One light ray comes in exactly parallel to the optical axis, and when it hits the center of the lens, it's diverted to go straight through the focal point. So that's one of my light rays. My second light ray can go straight through the middle of the lens, and it just keeps traveling straight. And then my third line will go from the top of my object through the focal point that's on the same side of the lens as the object. It hits the lens, and then it comes out completely parallel. And what we'll notice is that you get a nice straight line where all these things intersect, going down from the optical axis. That line represents the height of the image, HI, the height of the image. So the purpose of the lens is to recreate whatever your object is at a different position. And we're creating that image at a particular position. We'll call that DI, the distance of the image. This procedure we just followed, where we drew 3 rays, we drew the first one, which comes parallel, and then goes through focal points. We had a second one that goes straight through. And then we had our third ray, which goes through the focal point and then parallel to find where all these rays intersected. They all intersected on the opposite side. We drew a line from our optical axis down to represent the height of the image at a distance DI, the distance of the image. So we can take all of this information, we can take all these things, we can shrink down our little picture, and we can use this to analyze in the form of an equation, which we love in physics. We're obsessed with equations. So the equation we use to analyze this, there are 2 of them. We use the lens equation, which tells us 1 over the distance of your object plus 1 divided by the distance of your image is equal to 1 divided by your focal length. So that lets you figure out where these objects actually are relative to your lens. And then you also need to figure out how big your image and object are, something called magnification. The magnification is going to be negative the distance of your image over the distance of your object, which is also equal to the height of your image divided by the height of your object. So what this negative tells us, this negative is very useful. It tells us that our image is actually upside down. So when you see a negative, you are beneath the optical axis. There's some other sign conventions that we use. If the image and description conventions, if the image is on the opposite side of your lens, then we call it a real image. This kind of makes sense to me because I expect that light comes through a lens and is focused on the other side, so I'd expect my image on the opposite side of the lens. So I would call it real. If the image, however, is on the same side of my lens as the object, then I call that a virtual image. So these are all the conventions that you use when drawing these kinds of pictures and solving these kinds of problems. We call these ray diagrams. There are similar conventions that you use for mirrors, and I recommend reading about it in a textbook to figure out all these different kinds of rules and kind of make some note cards and try to start memorizing these kinds of things. There's some useful things in the OpenStax College Physics textbook resource, in particular on page 1014, that really help you with drawing more of these kinds of ray diagram images. And those are going to be section 25.6 through 25.8 that are going to be very useful in figuring out how to draw ray diagrams.